My name is Chris Thornton, and I'm the director of the Hydraulics Laboratory here at Colorado State University.
My name is Dane Palmer. I'm a graduate research assistant.
My name is Austria Fanner, and I'm a lab assistant at the ERC Hydraulics Lab.
My name is David Kulish, and I am the labor manager this summer at the ERC. So I supervise the labor crews for construction of the projects that we work on.
Here at the Hydraulics Laboratory, we work with a wide range of clients, from the government to local consulting companies to manufacturers of products that get used in a hydraulic environment. One project we're working on here is for Solmax, a manufacturer of erosion control protection devices and materials. We work with them in product development stages so that when they're developing new techniques or new technologies that they can employ in the civil infrastructure world, they have testing behind them, performance knowledge of where and how that product can be applied effectively. The Hydraulics Laboratory at Colorado State University is a unique facility in that we're able to draw water from the bottom of Horsetooth Reservoir. This allows us to run discharges in excess of 200 cubic feet per second through physical models that we construct to mimic designs and conditions in life that support the civil engineering design community. One of the most rewarding successes of the Hydraulics Laboratory at Colorado State University is the team that's been assembled here. From the technical staff in the faculty to the research scientists to the graduate students and undergraduate students that make up the backbone of our workforce, we're able to put together a work team that is able to solve very complicated, very unique problems for the civil engineering community.
During my time at the ERC, I've been able to take away a lot of experience and lots of hands-on experience with all kinds of different engineering practices. I've also got to learn a lot from my peers. That's probably been the most beneficial learning experience I've had, is just learning stuff from people and being able to really try it myself, and it's just been a really fun experience.
I've taken away a lot of engineering knowledge. Obviously, it's an intensive job for knowledge, and then also for physical activity. And I've taken away working with people better, and working with big projects, and just kind of seeing the process of how all of that comes together from the small the research side of things, and then also onto the development of the project.
The project we have going on right now with the Hydraulics Laboratory is with the Corps of Engineers, designing a flood control channel in an urban area in Puerto Rico. A very complicated system connecting the upland mountains to the ocean that has to pass through an area with multiple bridge crossings and curvature that is outside the range typically designed for. The physical model will be designed to help understand what that flow pattern is and what mitigation techniques would need to be employed. Particular interest for the laboratory with the Puerto Rico model is our construction technique. It's our maiden voyage of using a brand new method of constructing physical models. We have a computer-controlled router and a computer-controlled hot wire that we can route foam and cut foam to whatever topography a design may incorporate. It allows us to very efficiently construct the model and, more importantly, change in real time configurations within a model, whereby saving time and money for the client. We're currently working with AECOM on the design of Anderson Dam. The dam's being removed and replaced, and over the course of the 5-year period, there'll be a series of interim dams, each that has to protect against a potential flood situation for that season. Our job is to help define the critical components of each of those interim dams and provide a design that will withstand that potential for flooding.
So during the dry season, they're going to work and construct, and during the wet season they're constructing temporary spillways for water to spill over the top. And so we're creating the physical model for the two highest risk geometries, which feature 3-to-1 spillway slopes, transitioning to lower slopes down low. But those are the highest risk, and so we have that built in the 16-foot flume. And so there's two major components of the Anderson Dam testing. The 3-to-1 slope is going to be lined with articulating concrete blocks. And so that's going to create a stable surface and also add roughness. And so one component of the project, which I haven't been so involved with, is doing performance testing of the concrete blocks. And so that's mainly taking place in the steep flume, which is a 2-to-1 slope, and we are determining the roughness of the articulating blocks, the shear stress that they can withstand prior to failure, and then these blocks they're connected with wires, and so they're laid in mats, and so they want to be able to easily remove those mats and replace them from season to season. And so they wanted us to look at creating a grout mix that is easily removable. So they can just pull them out, put them back in, and regrout. And so we're also doing that in the steep flume. What I'm doing in the 16-foot, again, we have the 20-to-1 model, and so we're essentially recreating those two spillway geometries, running the design discharge, and as well as a few other smaller discharges to see how it responds. Essentially, one, does it contain all the flows, or do we need to change any of the design elevations? We're looking at the hydraulic characteristics, shear, depth, velocity. Also looking at if there is a hydraulic jump at the bottom of the spillway, where is it, and what the flow conditions are like at the main two slope transitions are at the very top, where it spills over the top of the spillway, and at the bottom, where it transitions from the 3-to-1 to a lesser slope. So we're also documenting that. But those are the main objectives of this study.
We've begun a new chapter here at the Hydraulics Laboratory in how we design and construct physical models. In the past, models were constructed out of sand and capped with concrete, incorporating wood and steel and plastic to be able to physically model what was being designed. Today, we're able to take LiDAR imagery, computer designs, and put them into a computer-controlled CNC machine with a router and a hot wire cutter that allow us to form our models now out of foam, so that we're able to incorporate very detailed topography and, most importantly, make changes in real time, so that it's very efficient to be able to go in and change a component of a design that's routed out of foam and incorporate evolution of the process of the hydraulic research.